Okay, so thank you so much, Ren, and also David, for inviting me. I'm very excited to talk in this format here about the work that our group has been up to within the last couple of years. Basically, how can we learn dynamic systems models from large-scale or small-scale data? So the types of questions that we ask are actually quite general. Yeah? So it's not confined to neuroscience, but more generally, whatever we develop or have developed in the last couple of years, you can basically apply to any type of time series or any type of system from which you have time series observations. So the general question is, can we just learn from time series observations generative surrogate model of the underlying governing equations, that behaves in several aspects like the original underlying system. So if we can do that, then we can use it for different types of things. We can use it for predicting certain properties of the system. We can use it for time series forecasting. But because we have a generative model or an approximation to the underlying governing equations, we can also dissect that model. We can use it for mechanistic insight, or we could, for instance, perform virtual experiments on it and use it, simulate new situations, use it for control, and so on and so forth. So that's our general goal. And our major background with this, for this is dynamic system theory. Since you are mainly a theoretical or computational audience, I assume that you are essentially all familiar with dynamic system theory. But I will nevertheless give a brief tour or introduction just to put everybody on the same page. So dynamic system theory is a beautiful mathematical theory that deals with the behavior of systems of, for instance, differential equations or difference equations. So very generally, if you have time series observations that evolve in time, an important concept in dynamic system theory is that of a state space here to the right, which you might loosely think of as a space spanned by all the dynamical variables of the system, or more precisely as a set of states in which these dynamical variables can be in. So on the left-hand side, you have different time series. So each time point would translate into a vector point in these spaces. And then as you trace out the time series, our vector point would trace out some trajectory in this space. So what we are then interested in are the topological and geometrical properties of these spaces, because these govern the fate of trajectories in these spaces. And in theoretical neuroscience, we sort of often tend to think that computations in the nervous system are implemented in terms of such trajectories and the properties of these state spaces. Okay, so the most popular concept that is probably familiar to all of you is that of an attractor, simplest type of an attractor are point attractors. So for instance, if you consider this simple circuit of excitatory pyramidal cells and inhibitory interneurons, often it's useful to think about dynamic systems properties as evolving from different interacting positive and negative feedback loops. So in this simple example of two populations of neurons, your state space would just be two-dimensional. It would be spanned by the firing rate of the pyramidal cells and those of the interneurons. And I've plotted the vector field here, which are just the right-hand side of these differential equations. So they give you where the magnitude and the direction into which a point will move if you release it at any point in the space. Let me actually see whether I can get a pointer here. No, that's not what I wanted. I hope you can see my cursor, but that's probably I wanted the laser pointer. Okay, so in this particular case, you see that the vector field is pointing either to this point at the lower left or to the point at this bottom top right. So activity is converging to this point if you release the system from different initial conditions in the state space. So this is a very popular model that has been introduced decades ago as a simple model of working memory by Wilson Cohen, I think. So you might recognize all this. So it might account, for instance, for delay activity, this property of bistability that you have here, and you will find some neurons in the prefrontal cortex, but also other areas that correspond to that. Okay, so and then very popular concept is that of these memory networks. One particular example are these ones introduced by John Hopfield in the early 80s. His Nobel Prize winning work, where he conceived memory patterns to be stored in terms of point attractors within these systems. However, I want to remind you that there's much more than point attractors. So in my mind, theoretical neuroscience has focused a little bit too much on just point attractors. So if you have interacting positive and negative feedback loops, you also often get oscillations. And stable limit cycles is another example of a type of attractor object in the state spaces. Yeah? So let me see whether I can play this video. I cannot do this if I have my laser pointer on. Okay, either way, let me see. Trying to run the a little video here, but it wouldn't allow me to. I convey is that limit cycles are another type of attractor object. As most of you will know, you can have limit cycles of different complexity with different periods. Like, for instance, if you have a bursting neuron, then your limit cycle will span different periods. And if you, for instance, change parameters of the system, you can also can obtain even more complex objects, attractor objects, like, for instance, chaotic attractors. And this brings me also to another point, namely that of bifurcation. So as you change different parameters of these systems, you can walk them through different dynamical regimes. For instance, from a complex limit cycle to a chaotic regime, back to a limit cycle. So the same system can exist in many different dynamical regimes based on its parameter configurations. And for all these types of things, you will also find some evidence in the nervous system. So more generally, I want to remind you that dynamical system theory is a mathematical theory. Yeah, so behind many of these concepts, there are strict mathematical definitions. So often we define an attractor very generally as any type of closed set which lives in some basin of attraction from which it attracts initial conditions. Yeah? So that will converge into the set, and the set can have it can be simple like a point attractor, but it can also be complicated, for instance, have a fractal geometry as in a chaotic set. Okay, and many types of attractor objects, you find some evidence in the brain. So, for instance, point attractors, just a stable resting potential of a cell, or persistent activity. Most of you will have heard about line attractors or manifold attractors, limit cycles. We talked about chaotic attractors, and then you might find many even more complex objects like this chaotic itinerancy that Suda has introduced, or this traveling between different ghost attractors. So there's a very nice paper out on that very recently, actually, by Koch and others in Physical Review Letters. Okay, so the point I simply want to make is that often in theoretical neuroscience, we think about neural computations as being implemented in terms of dynamical systems properties, such as attractors and transitions among them. Yeah? So actually, we might not even want to talk about attractors so much because often maybe the transient dynamics is much more important. Another thing that I just want to convey is that dynamic systems are actually Turing complete. Yeah, so whatever types of computations you are thinking about that you can implement with a universal Turing machine, you can also implement as a dynamic or reformulate as a dynamic system. Okay, so now the thing that our group is mainly dealing with is dynamic systems reconstruction. So what we mean by that is we want to retrieve from data the unknown underlying system. Yeah? So this is a simple example. This is a famous chaotic Röhrl system. So of course, in a real situation, we wouldn't usually know the system. We want to infer it from data. Yeah? So we assume that we have observed some time series from the system, and then we train some learning device on these time series. And most generally, we talk about neural flow operators because that's what we want to do. We want to approximate the flow of the flow operator of the underlying system. So the only thing that we demand is whatever type of deep learning device that is that it's a universal approximator. Yeah? So that whatever the underlying system is, we know that our reconstruction device can approximate the system. And for instance, recurrent neural networks generally have this property. And then after training, we want to be able to generate or to simulate new data from that trained system. And we would demand that they agree with the underlying system in the geometrical structure and state space, as well as in their temporal properties. Okay, so usually we request a little bit more from a dynamic systems reconstruction. So this is another example of a chaotic attractor, the so-called Vreeswijk attractor, with different initial conditions shown in here, yeah, from which trajectories are converging to this chaotic set. Now, in reality, we might only have a short trajectory, short time series, only from one initial condition. But we want to be able to infer the whole underlying attractor, for instance. Yeah, so indeed, in this case, this succeeded. In this simple example, we used a recurrent neural network. So it would, even though only trained on the short trajectory, it would authentically recover the underlying chaotic attractor. It would also be able to generalize to nearby initial conditions. Yeah, so usually we also ask for certain types of generalization to the long-term properties of the system, as well as generalization to other initial conditions in the same state space. Now, an important point that will be familiar to everyone who has some background in dynamic systems theory, but which in my mind has sometimes been overlooked in the literature on training recurrent neural networks, on empirical data, is a type of statistics you can use. Yeah, so usually the common type of statistics we use, like mean squared errors or likelihoods, yeah, or proportion of explained variance, are not appropriate to assess dynamic systems reconstruction. And so this is basically shown in this simple example. Yeah. So what I have done here is I just have drawn two trajectories from the chaotic Lorentz system with a minuscule difference in initial condition. And as most of you will know, in a chaotic, deterministic chaotic system, they will quickly diverge. Yeah? And that means that there's no agreement in the time series anymore, although both these trajectories were drawn from the very same system with the very same parameters. Yeah? So in dynamic systems terms, you would say, okay, I have a perfect reconstruction, yet mean squared error is not a good sort of currency to evaluate the properties of your reconstruction. Okay, so this shows this from another angle. So here you see in red the reconstruction, in blue the true system. So in this case, the reconstruction in terms of, let's say, the mean squared error is actually not so high compared to the right-hand side here. So on the right-hand side, you have a perfect reconstruction. Nevertheless, the mean squared error is larger, actually precisely because you do have a perfect reconstruction, which is also chaotic. Yeah, so you have these two systems diverging quickly, but on the left-hand side, although your reconstruction is not good, it sort of captures underlying basic oscillation of the system, and therefore it looks quite good in the mean squared error. But for instance, as measured by the state space divergence, it's pretty bad. Okay, so here is my sort of bit of tribute to Carl von Vreeswijk. The thing is that in my mind, and I would think also in Carl's mind, the nervous system almost inevitably chaotic. Yeah? So as soon as you put together a couple of heterogeneous elements, so they basically showed it in this similar 96 paper that and even simple type of neural network would have the tendency to self-organize into a balanced regime, and then it's almost purely chaotic. Yeah? And as soon as you the connectivity is somewhat random, or the elements in your system are somewhat heterogeneous, you almost inevitably get chaos. Yeah? So you need to deal with that if you are dealing with the nervous system. Okay, so we need to move to other types of statistics to assess our system. Yeah, so one I already mentioned in passing. You could, for instance, assess the overlap in geometry from your reconstructed system and your true underlying system. So the reconstruction is always in red, and the true underlying system, again, the chaotic Lorentz system in this example is in blue. You could also assess the agreement, for instance, in power spectra or in autocorrelation function. Yeah? So as quantified here through the so-called Hellinger distance, or you could look at other quantities yet that quantify your long-term temporal or geometrical structure. Yeah? The Kaplan-York dimension is another type of, it measures the fractal geometry of your attractor, or the maximum Lyapunov exponent measures the divergence rate. Yeah, so we need to go to other type of assessments if you want to confirm that we really have reconstructed the underlying system. Yeah, so just assessing the mean squared error is only valid on short time scales. Okay, so now our group mainly deals or tries to develop interpretable and tractable models. Yeah, because at the end of the day, we want to be able to analyze these models. So there are a lot of different architectures around there. Reservoir computing is certainly very popular. LSTMs are still quite popular, but please don't use them. And neural ODEs entered the scene a couple of years ago. At the end of the day, it's actually not so important which architecture you are using. In our minds, the training algorithm is much more important, and I will explain that, we'll flesh that out in the next couple of slides. So for these reasons, we focus mainly on relatively fairly simple models. Yeah, so our models are always piecewise linear. The sort of reasoning behind that is linear models are the best thing you can get. Yeah, so if you have a linear model, everything you can compute it very nicely, all its properties, but it cannot capture many types of interesting dynamics. Yeah, it cannot capture limit cycles, it cannot capture chaos, cannot capture multi-stability. So many things, computation concepts we would be interested in the nervous system, you cannot capture through linear systems. And so piecewise linear systems are sort of the next best thing. Yeah, so that's sort of our interest, and piecewise linear systems actually have a long tradition for these reasons, both in mathematics and in engineering. Okay, so this is our basic model. So it has this auto-regressive linear term, and it has this piecewise nonlinearity, also known as rectified linear unit. In the machine learning community, you might have a bias term, you might have external inputs, you might have a noise term. And often some neurons are actually surprisingly, I would say, piecewise linear in the input-output function. But that actually doesn't matter so much. Yeah, so you can consider this as a pure machine learning device. And then we couple this model, this latent dynamic systems model, through different decoder models, through different types of observations. But I will go into that into more detail later on. So over the years, we have developed different types of piecewise linear systems or models. Yeah, so sometimes, for instance, in these dendritic PLRNNs, we try to make the model more expressive while keeping this piecewise linear design. Yeah, so in this example here, paper by Manuel Brenner and Fleur and Hess already a number of years ago, we extended these nonlinearities in terms of these linear spline basic, piecewise linear spline basic expansions to sort of make the model more expressive. But you can show that you can reformulate models like this into this basic piecewise linear form. Or you might think of deeply or more shallow layered architectures. And more recently, we actually we even went a step back. We made this model even more simple and said, okay, let's kick out as many nonlinearities as possible. Let's keep only as few ReLU units in the system as are necessary to reconstruct the dynamics. And we call this the almost linear recurrent neural network. So the almost linear recurrent neural network actually has some quite nice properties. Yeah. So for instance, it turns out that it can reconstruct this chaotic Vreeswijk attractor with just one rectified linear unit. Yeah, just one. Yeah. So you only have two piecewise linear regions. Or the chaotic Lorentz system you can capture with actually only two rectified linear units. Yeah? So basically you only need three linear subregions for that. Okay, so what I mean with tractable is that, okay, because it's piecewise linear, you still have a combinatorial problem behind it, but we have very efficient algorithms for dissecting the topological structure within these systems. Yeah, so one of them is Sci-Fi, developed by Lucas Eisenman, Zara Montferrat, and others in our group a couple of years ago. So basically, we have closed form expressions for fixed points and cycles. The only thing is that you still need to make sure that the solutions that you determine to these equations are consistent with your linear subregions. Yeah, I don't want to go too much into the details about this. Just show an example. So for instance, here we have trained one of these piecewise linear recurrent neural networks on, in this case, in vitro recordings from a single neuron. So in black are your generated data after training. And I emphasize that these are not fits to the data, but they are simulated after we have trained on the data. And then you can use algorithms like Sci-Fi to dissect the structure of these models. So in this case, the model correctly captured that you have one stable fixed point corresponding to the resting potential, and you have one stable cycle corresponding to the limit cycle that creates a spiking activity. Okay, and with efficient, I mean that these algorithms scale highly efficiently. Yeah, so often they converge after linear time. Yeah, so the bottom line is a bit for piecewise linear systems, we have a lot of advantages because we can sort of semi-analytically compute different properties, and as a result of that, we can, we have very efficient algorithms that we can devise. So one aspect of interpretability is exactly what I just mentioned, that these algorithms are, that these models are tractable after training. Yeah, you can mathematically dissect them. But another is that, you can infuse biological semantics into them by, for instance, structuring their decoder or observation models in a certain way. And so this is our underlying latent model. As I mentioned before, we infer that from data by coupling it to different types of decoder models. And then you can read, for instance, these matrices like a conventional factor loading matrix. And for instance, if you find that different latent states or that different neurons load on the same latent state, then they might form a cell assembly. Or, for instance, you can constrain these coupling matrices in such a way that only certain neurons would couple to certain latent states, and then your underlying latent model would automatically inherit this sort of biological semantics in terms of, for instance, inter or intra-area connections. Yeah? So if your neurons come from hippocampus and prefrontal cortex, for instance. But you can also do whatever biological information you have, you sort of can infuse that into the model through through some constraints on your matrices. Okay, so how do we train these models? Again, I assume that basically all of you are familiar with gradient descent and with certain optimization techniques. So you have your observed time series, you have your underlying latent model. We'll cover that through decoder models, through our observations, and you take some quantity like a mean squared error or likelihood. And then, as many of you know, we'll have many different algorithms. In machine learning these days, we almost exclusively use gradient descent, where we move our parameter estimates against the gradients of our loss function. Okay, so a fundamental problem, as also some of you might know, is in gradient descent is this exploding vanishing gradient problem. Yeah, and that has bugged especially recurrent neural networks for quite a while. So one gradient descent algorithm is backpropagation through time, where you unwrap your network across multiple layers. And the essential issue is that as you propagate your error back across multiple layers, you get these exploding, you get from the chain rule product terms, and then it will explode or vanish. Now, or more formally, let's say you have your generic recurrent neural network. You consider the Jacobians, the derivatives with respect to all your states. And you want to train your system on, let's say, a chaotic benchmark or real data system. The problem is that these Jacobians also occur in the definition of the Lyapunov exponent. Yeah, so the maximum Lyapunov exponent is precisely defined as a geometric mean across a series of these Jacobians, and taking the logarithm of that. So for chaos, a necessary condition is that your maximum Lyapunov exponent must be larger than 0. Now, the problem is if you do your gradient descent, if you do your derivatives of your loss function with respect to the parameters of the model, then the same product series of Jacobians that occurs in the definition of the Lyapunov exponent also occurs in the derivatives of your loss function. Yeah, and so that inevitably leads to exploding gradients. Yeah, so the problem, especially for many empirical data, is that it's almost impossible to avoid exploding gradients regardless of the architecture that you use for training. So this is one of the things that gave impetus for us to develop different training techniques and put the focus actually on the training technique for recurrent neural networks. So assume that you have an observed time series. One of the ideas that we proposed a couple of years ago, mainly by Jonas Michael and Sarah Montferrat, is sparse teacher forcing. So assume that you have a set of observed time series. Your predictions from your model, let's say in the simplest case, is just given by a linear model that transfers your latent states into the observation state space. Then the idea is that from the observations, you can create a control series by inverting your, or pseudo-inverting in this case, your observation matrix. So basically what we want to do is we project our observations into the latent space and get a data estimate, inferred estimate of the latent states at any point in time, and that defines a control series. Now, in sparse teacher forcing, the idea is, okay, let's not replace every latent state at every time step, but let's do that once in a while. Yeah? So once in a while, we'll let the system progress in time, but once in a while, we will place the underlying latent state by a data inferred state. And then the question immediately is, so what's the optimal time lag? Yeah, so for how long should we let our system evolve before we force it back onto the real system, or align it back with the real system? Yeah, so the basic idea is, okay, you have these trajectories which are aligned at some point in time, but then you will give your latent system a little bit of freedom to evolve and to explore the future. But at some point before the exploding gradient problem sets in, you try to realign your system with the empirical system, and you force it back. And it turns out that this time lag you choose is actually crucial. Yeah? So in fact, it turns out that the optimal time lag is related to the maximum Lyapunov exponent of your system. Yeah? So if you're either too small, you basically prevent your system, your latent model, from exploring the future, and so you get a bad reconstruction. If it's too large, you run into the exploding gradient problem, and you get a bad reconstruction as well. So you need an optimal time lag, and you can sort of actually infer that from the Lyapunov spectrum. Okay, and I want to, with this slide, I just want to emphasize this is a real issue. Yeah, so if you take any out-of-the-box time series model and you run it on a dynamic system reconstruction system, it will problem. It might give good short-term predictions, but it won't give good reconstructions. Okay, so the more recent algorithm is generalized teacher forcing. It actually goes back to an idea introduced by Kenji Doya already 20 years ago. So the idea is instead of sort of forcing our latent system once in a while, we force it at each time step, but we'll take sort of a weighted average between the proof or the forward iterated state from our latent model and another state inferred from the data. Yeah? So we'll take a weighted average of this. And now the crucial thing here is the choice of alpha. We need an optimal choice of alpha. And it turns out that you can choose it in such a way that you completely abolish the vanishing and exploding gradient problem. Yeah? So again, the training algorithm here is of the essence, and that's basically what I want to convey here. Yeah? So actually the architecture is not so important. Yeah? So, but you need smart control theoretic algorithms during training if you want to obtain successful dynamic system reconstructions. Okay, right. This I want to don't spend much time on, but those of you who have trained networks yourself, and you instead of averages, you plotted basically the loss after each gradient update. You might have observed that you often observe these steep jumps in your loss, yeah? And that's actually due to bifurcations. You can show that empirically, but you can actually prove that. The point that I wanted to bring across that is that generalized teacher forcing actually also avoids bifurcation. Yeah, so it sort of manages to sneak around bifurcations. Yeah, so with DTF you often get relatively smooth loss curves, and to avoid all this jumping back and forth across these bifurcations. And for certain types of bifurcations, you can make this point exact and can actually formally prove that. Okay, so this shows some ground truth examples. Yeah, so if the system is not chaotic, like in this bursting neuron example, you might get a precise overlap of time series. If it's chaotic, you don't get that. But interestingly, here, for instance, the system would often, and if you have a reconstruction model, it would often, and you use one of these training algorithms, you can often infer other properties in the state space that your system was not trained on. Yeah, so for instance, here, correctly recover the approximate location of the fixed points, although it was not trained on that. So this is a higher dimensional example, Landau-Sompolinsky model, neuropopulation model. It's also chaotic. And we did this for many different empirical examples. So this is, for instance, fMRI observations, both time series. This is the overlay in power spectra. On the right-hand side, the overlay in the state spaces. And once again, I emphasize that these are not fits to the data, but these are reconstructions. Yeah? So that means we'll just estimate an initial condition from the data, and then we just simulate new data. Yeah? And that's what we put on top of each other here. So this is another example, simulated and true EEG data. You can do this with single neuron recordings. In fact, over the years, we did this with many different types of data, calcium imaging, or this is an example of smooth human electrocardiogram data and model simulated data. You can even do that with more complicated data, like behavioral assessments, with climate data, and so on and so forth. So these models are actually quite general. Yeah? You can throw them at any type of data that you have. Okay, so now let me go into a bit of a different topic. Again, I don't want to go into much detail about this because I want to spend more time on foundation models. So many types of data evolve on many different timescales. Yeah, for you, neural data, that's certainly true. You have many different time constants in your systems. Yeah, you have things that evolve on the order of milliseconds and other things that evolve across minutes. Yeah? So what we used is, or the idea here was, we wanted to keep our simple piecewise linear design, but we wanted to encourage the system to capture many different timescales. So you want to see this, might want to see this as a neuro-inspired architecture. So what we did is we basically encourage a manifold attractor configuration in the system through a regularization term. Yeah? And if you slightly detune a manifold attractor, then you can basically essentially capture many different timescales. Okay, so the key point here is we didn't touch the architecture, but we implemented a regularization term. We added a regularization term that would automatically push some of the latent space towards the manifold attractor configuration. Okay, and that architecture you can actually show you can outperform on these long-range arena benchmarks many other architectures, including LSTMs, while keeping the simple model design. Yeah, this is important. Okay, so I assume I have a problem here with my video. Yeah, so I think yeah, I will skip it. But basically, it shows you a video. You can also look it up here in the internet of a recurrent neural network fit to a bursting neuron model example, and then you can see nicely that certain states specialize on the spiking activity, and other states specialize on the slow underlying oscillation. Okay, so now let me come to reconstruction from multiple data modalities. Yeah, so often you have many different data modalities observed simultaneously. Yeah, so for instance, in neuroscience, you might have categorical behavioral data, like just the choices of an animal. At the same time, you might have your calcium imaging recordings, or you might have your spike counts. Yeah? So the question now is, okay, can we reconstruct dynamic systems just from spike count data, which are not continuous, or can we reconstruct from many different data modalities with different statistical properties simultaneously? So for that, Manuel Brenner and Florian Hess in our group developed this nice idea of multimodal teacher forcing. So here the idea is that we use the multimodal variation order encoder to basically construct a common latent code from many different simultaneously measured data modalities, but then different from a sequential variation order encoder that you might have heard of. We don't embed the recurrent neural network directly in the variation order encoder. Rather, we want to use output from the variation order encoder as a forcing signal. Yeah? So that goes back to the teacher forcing ideas. We want to use sparse or generalized teacher forcing as before, but now we want to combine different data modalities. And so we do that through a multimodal variation order encoder, which then guides the reconstruction model like a recurrent neural network in training. Now, the only essential thing that you need to take care of is because you have now two latent codes, one from your multimodal variation order encoder and one from your reconstruction model. So you need to make sure that these are consistent. And we do this by coupling these to the same set of decoder models. Yeah, so all the decoder models for the variation order encoder and the reconstruction model, they share the same parameters. Yeah, so they couple to the same set of reconstruction model of decoder models. And also in the loss, we have one term that enforces the consistency of the two latent codes. Yeah, actually nicely just pops out as a prior of the probability of the for the multi-modal variation autoencoder. Yeah, so the prior distribution for that, if you take that to come from your reconstruction model, then it automatically gives rise to the form. Okay, so here's an example. Yeah? So at the bottom, we have generated spike trains after training. So this is from an open source data set from the Vreeswijk group. And at the top, we have a set of spike trains that we haven't used for training. Now, so the only thing that we use is an initial condition inferred from the data. And then we also use the same inputs, in this case, the reward inputs that the animal has seen. Yeah? But otherwise, at the bottom, it's purely simulated activity on a test set that has not been used for training. So you can quantify this. Yeah, you already see by eye that there's a pretty good agreement between the generated, the simulated activity and the true physiological activity in the test set. But we can also make this more formal by, for instance, quantifying the correlation between different spiking statistics between the generated and test activity. So these are all the blue dots here, and you see that they quite highly correlate. In fact, they correlate about as highly as you would, as if you would take different segments of the real data. Yeah? So if you take the training and the test set of the real data and correlate them, and the agreement in your different spiking statistics is about as good as to the generated data. Yeah? So this essentially confirms that our reconstruction model is as good as it can be in the limits of the noise that you have in your real data. You can also predict the behavioral position very well, and you also get a common latent space, yeah? So that embeds, or an interpretable latent space that embeds both the behavioral and the neural activity data. So this is sort of similar to Zebra, only that on top of Zebra, you get a generative model of the underlying dynamics. Okay, I think I have about 10 to 15 minutes left. Maybe just briefly, you can also adapt these models for non-stationary time series. So this is an example from recordings from Florian Berner from our group, and analysis by Max Thurm. So it's a rule shifting task where the animal learned one rule, and then unknown to the animal, the reward contingencies were changed, and the animal had to figure out by trial and error the new rule. So this is a typical example of a highly non-stationary task, because the animal is learning something. Yeah, it's shifted to a new rule, and you would expect that also the underlying neural activity is non-stationary. Now, I should emphasize that the models that I have shown so far, they don't have any problem with non-stationary systems or activity, but for means of interpretability, we decided here that we also want to make the parameters of the system non-stationary. Yeah, so we sort of assumed that okay, there might be some restructuring of the underlying weight matrices. So we basically allow each trial its own weight matrix, but then we tie these weight matrices together by a smoothness prior. Yeah? So we force them to be close to each other and don't allow them to just arbitrarily jump around. Okay, so this is again some reconstructed activity of neural firing rates, or the choice behavior of the animal here to the right. And usually you find in these types of recordings change points. Yeah, so the from one trial to the next, your neural representation might jump to a different one representing the new rule. And we also find that the recorded and the change point in the generated activity nicely agree. And then you can basically zoom into more detail. Yeah, so you can just look into the weight matrices, how they restructure across trials. And one thing, for example, that we found here is that the restructuring of the underlying connectivity always, or most commonly, would precede the change point in the behavior. Okay, now one important step that I now want to take is going to animal data. Yeah? So let's assume you have not only many different data modalities that you have recorded from simultaneously and that you want to integrate into the same model, but you have many different animal subjects that you want to integrate into the same reconstruction model. Now, the idea from Manuel Brenner and Elias Weber was, okay, it's a bit similar to what you find in large language models. When you fine-tune large language models, one of the techniques is this low-rank adaptation technique. So the basic idea here is somewhat similar. We'll split the parameters into group-level parameters that are common across all animals, and preferably very low-dimensional, subject-specific vector. Yeah? So we have some subject-specific parameters, and we have high-level, group-level parameters that are shared across all subjects and that exploit the commonalities in the dynamics across subjects. And then the idea is, okay, we'll have some function parameterized by these group-level parameters that maps our subject-specific feature vectors onto the parameters of a subject-specific reconstruction model. Yeah? So despite the joint training on many different animals or subjects simultaneously, at the end of the day, you still get a subject-specific reconstruction model that you can run and analyze for each specific subject. Okay, and then we train this all end-to-end in one common framework. Now, so this is just examples on benchmarks. Yeah, so you get these different dynamical regimes that you can nicely reconstruct with the same underlying model. What I want to emphasize more is, and what was a bit of a surprising result to us is that, so in these simulations, what we did is we varied different ground truth parameters. They are like this rho or this c. Yeah, these are control parameters in the differential equations of these systems. And what we found after training is that the features, often in a highly interpretable fashion, even often in a linear fashion, correlated with the underlying ground truth control parameters that we varied. And you can also show that for more complex systems. And so this here, for instance, is an example of human of a simulated of a set of simulated biophysical equations, high dimensional for human ECG. And once again, you often find this almost linear relationship between features extracted that determine your subject-specific models and control parameters of the underlying ground truth system. Yeah, so it means that automatically this approach seems to extract parameters, features from the systems that have some semantics, that have semantics in terms of control parameters. Okay, and this feature actually also allows some out-of-domain generalization. Yeah? So here, for instance, we trained on a certain regime enclosed here by these dashed green lines, and then we can also, to some degree, extrapolate beyond this training regime. I won't go into this very much. You can also use it for fine-tuning. Yeah? So it turns out that these types of models, you sometimes only need up to 100 time steps, let's say, to fine-tune on a completely new animal. Okay, so there's another interesting outcome here, and that is that we observed that, because you now have these feature spaces on top of your subject-specific reconstruction model, this gives you another perspective on the system. And you can also now analyze these feature spaces. And it turns out that dynamics which are close to each other will cluster in these feature spaces. So in this particular example, we trained these models on EEG recordings from epileptic patients and healthy controls. And you can see that the healthy controls and the epileptic patients, they all tend to cluster in these feature spaces. Although this is completely unsupervised, I should also emphasize this. Yeah? So we don't use any class labels in here. Yeah? So this is completely unsupervised approach. And to put this into perspective, this works much better than with any other time series classification tool that we tried. Yeah, so there are many popular ones like rocket features or Cat22 features, or attention convolutional autoencoders. So it seems that the dynamical systems features that you extract through these types of approaches actually work much better than classical time series features, also for doing some sort of classification analysis in these feature spaces. Okay, so this is most recently, this is one bit that Christoph Hammer did from our group that we will submit to NeurIPS in a few weeks. So this is an architect. So you can already see these architectures get more and more complicated, but they can also do more and more different types of things. So in this type of architecture, we use it's a mixture of experts architecture that are quite popular for reasoning models, for instance. So you have different recurrent neural networks that learn to become experts in the training, and then you have some gating network that basically during runtime decides how to factor in different of these experts. And this is an example where we actually could obtain zero-shot reconstructions of dynamic systems. So with zero-shot, I mean, we just present a little bit of context. Yeah, so this is in purple here. So this is a time series we give to the trained system, but we don't retrain it on this context. Yeah, so we don't fine tune any parameters. We don't retrain it. We'll just provide it as a context. And then the task of this network is to predict or to do an entire dynamic systems reconstruction, yeah, including power spectrum, state space, and everything. And so it's needless to say, this is an example of an attractor that was not in the training set. Yeah? And in this example here as well, although we love the Lorentz, we always have it in the training set. In this example, training here, it was not in the training set. Yeah? So we'll just presented the network with a little bit of context from this previously unshown example, and then it did a zero-shot inference of the underlying dynamic system. Okay, so with that, I'm actually at the end. Yeah, so what I try to convey in the first part is dynamic systems reconstruction. We desire certain properties, and we need to ensure that we really have these properties after training. I showed you our multi-modal architectures, mainly developed by Manuel Brenner in the group. And I illustrated these steps towards model, which we are actually now actively training as a foundation model on many different types of neural data sets. And with that, I just want to introduce briefly our group. Major driving forces between the algorithm development were Manuel Brenner, these different types of teacher forcing, multimodal, generalized teacher forcing, and so on, Manuel Brenner and Florian Hess. Christoph Hammer was involved in the mixture of experts that I have introduced at the end. Zara Montfred, for a long time, was sort of the chief mathematician in our group. So she developed much of the mathematical background for many of these models, and luckily has her own AI research group now in Heidelberg. Max Thun has worked on many of the empirical data. Roger Koppe, meanwhile, also has her own professorship in Heidelberg. She has worked a lot on clinical data. And Jonas Michael, I also already mentioned in passing. So thank you very much for your attention. With that, I'm at the end of my talk.